So how many of you use apps on your commute to work? Like probably most of us, right? If you're like me and you live in London, you may ride something like the tube and you just don't have connectivity inside on your commute to work. But even if not, like you can't guarantee a signal all the time in a mobile smartphone environment, right? Like maybe you're just driving through a dead zone. Maybe you're walking in a city street and the buildings get in the way. So it's important to think about connectivity as not always a given. And so Gopal is going to talk to us about how to build apps that are great with an offline-first mindset. So please welcome Gopal.
Hey, how's it going? Good? Everybody have a good lunch? All right, all right. So first off, thank you all for being here. I know it's a beautiful day outside. Might have questioned would I be here. All right, so before we get started, just a quick show of hands. How many of you here are designers? Designers? Okay, a lot of you. How many of you here are developers? Some of you are obviously both. All right, cool. All right, let's get started. So let's start this talk by defining what I mean by an offline-first app. So obviously, part one of this definition is obvious. It's apps that work without an internet connection, right? But that's not sufficient because let's say you have a recipe book app that saves recipes on the phone and never actually interacts with the server. That's just an offline app. It's not an offline-first app. So the second part of this equation is it has to have the ability to catch up to a server later on, right? So you should be able to use the app with other users, with your own data on other devices, and still be able to use it when there's no internet connection. So that's the definition we're going to work with today. So the best way to clarify this is perhaps to start with an example. And a good example is the Notes app that you have on your iPhone, iPad, and Mac. So show of hands, how many of you have used these apps? Okay. How many of you have used them since it moved over to CloudKit? And how many of you used them before? Anyone before? Okay. So then you know exactly how terrible it was before and how good it is now. Right? Okay. So I know you've had a healthy lunch, so I'm going to play a video next. Pay attention to it, and let me know if you need me to play it back. So what's going to happen next is I have an iPhone and an iPad. Both of them are in airplane mode at this point. And you can see that I'm very creatively taking a note on my iPhone when it's offline. And of course, nothing's really happening on the iPad because they're offline, right? So we're going to switch them back to being online. There we go. And instantly, kaboom, it's over there, right? And once again, we're going to go offline and pay attention to how I'm going to make a mistake here when I edit the note on my iPad, right? So I'm typing, I'm going to fix a mistake and keep going. That's important in a second. All right, so again, notice that we're still offline, so there's no changes that are reflecting, but I could still use both apps at the same time, right? And once I go online, notice how the changes animate in, right? So you know they animate in two chunks, right? And that's important later on, okay? So this is sort of the definition of a prototypical offline-first app, where the core features of the app work even when you're offline, right? But some features obviously make no sense to work offline, like the actual moving of data between the two devices, right? So let's say, for example, you want to share this note. That's not going to work if you're offline, because obviously you need to be online for that. But it's not like, for example, say, an app where if you're not online, you can't do anything with it, right? So before we get into how we build these and what the problems are, let's first ask ourselves the question of, should we even be doing this? Why? Because networks are pretty ubiquitous these days. You know, almost everyone here has a 4G connection, if not on the Wi-Fi. And as you'll hopefully figure out in the next 30 minutes or so, being offline first is really non-trivial. There's a lot of problems. And of course, you may not need to be offline first, right? So for example, if you're building a stock trading app, it'd be pretty silly to have that be offline first, because you don't want to give users old data. They may make decisions based on that that'll end up damaging them overall, right? So unless you need it, don't do it. Take it from someone who's done this many times before. So now that we know why we shouldn't do it, let's actually get into why we should do it. So first, I know we just said networks are pretty ubiquitous, but they are still pretty crappy in a lot of cases, right? So in a lot of situations, networks are either slow, flaky, or expensive, right? So a good example of this is just me. So when I'm back home in India, I have a pretty good network connection more or less wherever I am. I have fiber in my house, I have fiber in the office, my 4G is reasonably good. And it's also pretty cheap. But now when I'm in Spain, I don't know what the hell kind of plan I'm on, but it's slow as hell, right? So it's pretty expensive. Second, I don't know how much of a problem this is in Europe, but if you've lived in not the urban parts of the United States or not the urban parts of India, you'll notice that networks are really, really unreliable in rural parts of the world. And there's a lot of parts of the world where this is true. Right? And even in modern civilization, networks are not as pervasive as we think. For example, how many of you got here on an airplane? Almost everyone? Yeah. You probably didn't have access to a network on that airplane, right? And you still wanted to get stuff done. Basements, right? They're the worst. And we end up in them more often than we'd like. Elevators, another one, right? And this one was a new one for me. We were developing this app that's predominantly meant to be used in hospitals. And turns out that all the stuff that they have in a hospital is pretty terrible for reception. So you're not going to have a network connection at all, for the most part. All right, let's look at some numbers. Just show of hands, how many of you have seen this truly terrible TV show? I hope no one here wrote it. Okay, for the rest of you who haven't seen it, don't see it. So, important number. This is the distance as the crow flies from my hometown, Bangalore, to San Francisco. Why San Francisco? Because a lot of the internet is there. 14,000 kilometers, pretty big distance, right? Now, let's say we could travel at the speed of light. Anyone want to guess how long that would take to travel 14,000 kilometers? Don't worry, I did the math. It's 47 milliseconds one way, right? At the speed of light, if we wanted to traverse 14,000 kilometers, it would take this long. Now, of course, this is making an assumption that you actually have one fiber optic cable from point to point, which is not going to be the case. So in practice, Verizon claims that their connection from India to North America is about 240 milliseconds latency on average, right? I don't know what Verizon is thinking, but when I did my own test, that number is closer to 360 milliseconds. I also did this test from my hotel room and on my cell phone, and I don't know why. It doesn't make sense. It should be smaller in Spain, but it's actually larger in Spain. I don't know why. Now, let's compare this to another number, which is the latency that your flash storage on a phone is going to have. That's typically 0.05 milliseconds, right? So it's several orders of magnitudes less. Now, I know this annoying guy who keeps saying this all the time. You should never wait for your phone should wait for you. The annoying guy is me. So if we do this, one of the benefits we get is obviously a better user experience, right? So there's these folks at Microsoft who a while ago did a bunch of research, and there's a link to a YouTube video down there, where they more or less sort of started moving their finger on touchscreens that have different latencies. And they noticed that anything at about 100 milliseconds or more is when it feels like you're waiting for the hardware, right? Anything less than that, you're starting to get better and better, right? So if you're looking at that, and the fact that typically, if you're dependent on the network, somewhere between 300 to 500 milliseconds is the latency you have, you're going to end up with slow apps. And of course, nobody likes slow apps. Now, for whatever reason on the web, people are sort of quote-unquote OK with stuff being slow. But if WhatsApp was slow, nobody would use it. So now that we know why we're going to build offline-first apps, let's look at some of the challenges. First, conflicts. The minute you have multiple devices and a server, you're going to have conflicts to deal with. Second, inconsistencies. So for the developers here, if you're familiar with typical ACID integrity and that sort of thing that databases give you, this becomes a lot harder when you're doing it across devices. Third, error handling is really messy. And fourth, getting optimal performance is not obvious. So let's get into the details of each of these things one at a time. Starting with conflicts. So I'm going to try and tell a story as time goes on here. So to start with, let's say that we have a server and two devices, okay? Device A and device B. And at, say, some arbitrary time, say 9 o'clock in the morning, all three of these have a note, and let's say that they all have exactly the same content, which says note 1. Right? With me so far? Right? Now, let's say at 9:01, both the devices go offline. Okay? At 9:02, device B says, I'm going to modify that note and add the text device B underneath it. Right? And obvious next step, at 9:03, device A says, I'm going to also modify that same note and make it device A. Now, let's say at 9:04, device A goes online, and it's going to try and push that data up to the server, right? At which point the server says, OK, great, now I think it's device A as well. But then device B goes online at the next minute, and now what are you going to do, right? What should the server think? What should device A think? What should device B think? It's not obvious. And regardless of what you end up doing, you have to answer this question of how do these three distinct devices get the same data, right? So what are some options? First, pick one, throw the other away, right? Fairly obvious. Another one, duplicate them and keep both of them, right? So you just make a copy and say, my note is now 2 notes. And the third one is you find a way to combine them into one version, right? So let's start with each of these options. Pick a version, right? So obviously this is bad because you end up with data loss. Regardless of what choice you make, one of those copies is going to get thrown away, right? And that would more than likely result in some form of data loss. Now, even if you said, it's OK for me to have data loss, I don't care, you have to ask the question of which one are you going to throw away, right? And good answer would be throw away the first one, pick the next one, right? But then how do you decide which one was the first one? Okay, obvious answer, let's look at the timestamps, but obviously you can't trust client-side timestamps because people could be on different synchronizations with the time clocks, right? So you can go into your phone and change the time, right? And obviously there's also clock drift to contend with. Now, you could say we'll use the server timestamps, but the problem with that is, A, if you're offline, the server is going to receive the events at different times, so you can't trust that either. And if your server is itself a distributed system of some sort, even those timestamps can't be trusted in an obvious way unless you're manually synchronizing them somehow, right? So this is no good. So instead, let's consider the duplication version, right? So the good news is there's no data loss, right? Everything's still there. But it's going to get annoying soon enough, right? So if each time you end up using your apps offline, if you end up duplicating data over and over again, the onus is on the user to go clean up that mess after you, right? Which is fine, but it's not ideal. So obviously what we want is to combine these in the same way. The question, of course, is how? The unfortunate news is there's no generic answer to this question. There's nothing you can really do that would work across all your apps and across all the domains, right? And we'll get into why that is shortly. But there are a few options that, depending on the context you're in, could work. So first, show of hands, how many of you have heard of diff3? Diff3? Few people? OK. If you're a developer, you've used this because Git uses it underneath the hood. So I don't have time to get into what diff3 specifically does, but it's a way of taking 3 versions of the same content, provided the content can be structured as a list of objects and merging them together, right? A slightly more sophisticated option is CRDTs, or as they're called, conflict-free replicated data types. Again, there's papers here that are linked to, where you can go learn more about these specifically, but the general idea is these are ways of ordering a sequence of events in a predictable manner. Note that I said predictable, not sensible. Right? You may still end up with nonsense at the end of using these algorithms, but at least you will end up with the same nonsense on all the devices. Right? If you're curious, the Notes app uses CRDTs. OK, so we think we have a solution, right? But it gets worse. Let's look at this example of calendar. Right? So let's say on one particular device, I've got this data on an event. For those of you who aren't familiar with UB City, which I'm assuming is none of you, it's a very popular mall in my hometown where there's a lot of restaurants, fancy place, right? So we'll say we're going to do a celebration dinner, right? And on another device, we go and change that to funeral at Cemetery Road, right? Now, I'm assuming you can predict the next thing, which is you do a funeral at UB City, Or worse, you end up doing a celebration dinner at Cemetery Road. Right? So there's sort of two ways you can think about this problem, right? One is that you can say that, hey, I don't ever want the user to see a conflict, right? So I'm always going to write my programs in such a way that I'm going to make that decision for them. Unfortunately, when you try to do those things, you end up with this. The other option is to make the user choose what they want, but do it as little as humanly possible, right? So the first approach is ideal because nobody wants to be annoyed with dialogues that say, hey, fix the conflict. But the second approach is more of a belt and suspenders approach. Right? So it depends on your app in terms of what you want to do. Obviously, some domains lend themselves to automatic resolution more than this. This is a particularly bad example because there's no way for you to know the relation between the two fields. Right? All right, conflicts are done. Let's talk about inconsistencies. So even in situations where your records are conflict-free, you can end up in a situation that between records, your data doesn't make sense. Right? So let's look at an example again. This is an app that we're building. And the idea here is that we have these blocks of time, right? And each block of time for us is a timer record. And a timer record has a start time, it has an end time, and it has a project ID. And that's what the colors end up meaning, right? So you have a situation like this. We've decided that no human being can be doing two things at once. I know. So we want to make sure that we don't ever end up in that situation. So it's possible in this app where none of the records are in a state of conflict. All the devices agree that they're in sync and everybody has the latest version. The problem may be, though, that between records there's a lack of consistency. So for example, you could end up in a situation where, say, I have a project from 9 a.m. to 10 a.m. and another one from 9:30 to 10:30. So here there's a 30-minute gap where between records the data doesn't make sense. Right? And you have to find a way to figure out how do I get that integrity back. Right? Cool. So that brings us to the next problem of how do we build consensus. Right? So you have multiple devices. Could be for the same user, could be for multiple users, depending on your app. You have the server. In some cases, you can have more than one server. So what are the options we have for building consensus? Show of hands, how many of you have used SVN? All the old people. Cool, all right. So one option is to do what SVN does, which is sort of say there's a universal source of truth, and that's the only one that wins anything. The other option is to do something more akin to Git, which is sort of a distributed truth, where each person or each device has their own version of the truth. Now, you might think that Git would be the way to go, given that SVN is dead or whatever, but the reality is most of us who use Git use it just like SVN. I mean, how many times have we said GitHub is down, I'm not going to get any work done, right? So what I'm going to do is next walk through what CloudKit does, right? So all of what I'm going to tell you is documented in a paper that was written by Alexander Schreer. So we'll get into some parts of the paper, not the whole thing, right? OK. So like all good programmers, we'll start with a zero index of time t0, right? And we're going to try and model how notes would sync. So for the purposes of this conversation, let's say that notes have a few fields. They have an ID. They have a change token. I'll get to what that is in a second. They have the text of the note and possibly a bunch of other stuff, right? Now, time t0, what happens is you have two devices and the server, and they're all in sync in that they agree that there is one note, the ID is 1, the change token is 1, and the text is ABC, right? So the change token, think of it sort of like a version for that particular record, right? So what happens next is at time t1, let's say device A edits that note, and you now end up with text ABCD, right? And at t2, it sends that to the server, right? Now, when it sends that to the server is going to look at that request and say, OK, you think you have change token 1. I know that change token 1 is the latest version, so I'm going to accept that change. So it's going to update the server copy to that, right? And send back a response saying, OK, now this is the new version. It's got the same text, but the change token is updated, at which point device A says, OK, cool, I've got that too, so I update my copy as well. Now, at time t3, when device B was offline, it said, OK, I'm going to modify that note to be ABCE, right? And try and send that to the server. Now, the server is going to say, hey, you think you have change token 1, but I know that the latest one is 2, so I'm going to reject this request. And it's going to end up rejecting it with three things. First, the version of the note that device B sent it. Second, the version of the note that's the latest version according to the server. And third, the common ancestor between the two, right? So the reason you need these three versions is a lot of conflict resolution algorithms like diff3 and most CRDTs need all three, right? So what device B is going to do with that is do the conflict resolution using one of many techniques. One could be really simple and say, hey, make the user do it. Or you use something like diff3 or CRDTs, and this is roughly what diff3 would do, is you create a new version of that note. It updates its local copy of the change token because it has resolved the conflict. And then it's going to send that back up to the server, right? And this time, the server is going to see that device B actually has the latest change token. So it can now say, cool, that works. And device B will update its copy there, right? Cool. Now, of course, the question is, how does device A get to know about this? And that's pretty simple. So what device A is going to do from time to time is say, OK, give me the latest records since the change token that I know, right? So it knows that the latest change token is 2. So it's going to ask for everything since 2. The server is going to say, OK, I have 3. So here you go. That's 3. And device A updates itself locally as well, right? So this mechanism, you found a way to effectively achieve consensus across devices without ever relying on timestamps for anything, right? The server's change token is effectively our definition of time. Make sense? All right. Next topic, error handling. So in typical traditional apps, what you end up doing is dealing with errors in two possible ways. The easy way is when you're dealing with synchronous methods, and the code looks something like this. For the Swift developers, this should be fairly obvious. For Kotlin developers, it's there or thereabouts. But the general idea is you have a function that can do something, and maybe it ends up with an error, in which case you either throw an error, or you return some sort of sentinel value that says, OK, this didn't work, right? These are probably one of the most common ways of dealing with errors in most synchronous code, right? Another way to deal with them is in asynchronous code, right? So let's say you're doing something like making a network request. What you typically do is give a callback of some sort, right? And maybe you don't actually use a callback. You instead use something like RX or some sort of promises mechanism to make this look nicer. But the general idea is the same, which is that you're calling an asynchronous function. When it has a result, it calls you back. And that callback has either a success value or a failure value, right? And you deal with it appropriately. Now, let's think about how this would work when you're dealing with offline apps. So let's say, again, that I have a device A. And let's say, again, that this is a calendar app, and we have this event saying dentist appointment at the dental clinic. Then you have on the same device, I save that and move to a different screen. Right? So maybe I'm looking at my list of calendars. I don't know why I would do that, but let's say I'm doing that. And then on device B, I go and edit that to say dentist appointment at barber shop. Right? So the question now arises, what exactly is A going to do? Because it no longer has the UI up there that would have allowed you to show the conflict to the user. Right? You're probably on a different screen. You could even be out of the app altogether. Right? You could have closed the app, moved on, and your sync is triggering in the background. Right? Either because of a remote push, or maybe you have a background fetch turned on, or something like that. Right? So how do we deal with this? One possible solution, there's many, is persist errors in the database, right? So if you stick, in addition to your results, the errors in the database, those errors stay until you get rid of them yourself, right? And one way you can use those is create an observable that would fire whenever an error is found. So for those of you who are not familiar with the RX or reactive world, an observable is just something that can observe the state of some data and emit function calls whenever something changes, right? So you don't need to use an observable, but the general idea is that you monitor those errors for occurrence and then keep firing events whenever they happen. And then you make common UI for each type of error to get the user to resolve it if they need to, or if you can resolve it automatically, you do that instead. And of course, you would have to be intelligent about how you opt users into resolving those errors, because not every screen in your app is probably going to want to have that capability, right? So if I'm, for example, in my settings screen, I probably don't want to be interrupted with, hey, please resolve conflict, right? Or if you're about to, say, make a payment for a subscription, that's not the time when you want to interrupt a user. And of course, don't forget to remove the error from the database, because otherwise it's going to keep coming back up. All right, the best part about this, too, is remember we talked about inconsistencies? This model would work for that, too, because all you really need to do is say, every time I insert a record into my database, look for whether that would create an inconsistency, and if so, write the error right there. All right, let's switch topics again to performance. So the obvious question here is, how do you move data between devices, right? So obviously, we can't just keep sending the entire data set back and forth. It could end up being pretty large, so you don't want to do that. So you have to sync deltas, right? So the idea is you only want to get the data that each device doesn't already have. So the way CloudKit does this is with something called forward sync, right? So the idea behind forward sync is that you start at, quote-unquote, the beginning of time and start retrieving records one at a time until you catch up to the latest present, right? The advantage of this is that you can just keep going, and even if you need to paginate your requests because you have too many of them, you can just keep going until you're done, right? So that's fairly simple. And the idea was exactly what we talked about before, which is, let's say you have this situation where device A is behind what the other devices know of. What we do is simply make a request saying, get me all the changes since a particular point in time. You get those responses back, and you are now up to date. Right? So the advantage here is also that you could do this in a reverse sync, right? So say you're building a messages app where the device first syncs, you want to do it in a way where the latest messages show up, not the earliest messages. You can do that too, where all you need to do is start syncing backwards from now until the very first record. But the trick there is you have to make that sync change token work such that once you've gone back to the origin of time, you resume a forward sync from where you started. Make sense? All right. Now, of course, no developer talk would be complete without an architecture diagram. I would love to have come up with an acronym for this, but I don't have time for it. So general idea is that this is what the read path of your app would look like. So say you have a database locally, you have a store object in front of it, and you're observing changes to that database through Rx or anything that does a similar thing. And the store would effectively yield observables of either your view data, in this case, the view data is what you'd show on screen, or if you have errors to resolve, you would show that instead. And the view controller's job here, and for those of you who are Android developers, replace view controller with activity/fragment, and it would just simply pass the data on to the views. Right? Okay. On the right side, again, fairly simple. The views would emit events to your view controller. The view controller's reducer would convert them into various model object changes, which would go to the store. The store would then push them to the database. Right? And of course, that brings up the question of how we're going to sync all this data. So the general idea here is the linchpin of this mechanism is going to be a sync manager. The view controller in this case is sort of calling start sync, but the idea is that's a fire and forget, right? So anything in your app could be something like, for example, your app has entered the foreground, trigger it. So it's a fire and forget. The sync manager would be responsible for doing things like making sure that you're not unnecessarily syncing. So for example, if maybe you've synced 5 seconds ago, you don't need to do that again immediately. You can queue that for a later time. The sync manager then goes to the store and says, hey, what are the model objects that need to be updated on the server? You push them up to the server through an API client of some sort, and use the same API client to get the updated version from the server and write it back to the database. Right? Now, the nice part about this is this can run completely in the background, right? So it's not dependent on your UI at all, right? It's a nice thing. OK, so let's quickly talk about libraries and tools that we use to do this pretty well. On iOS, I'm a huge fan of this library called GRDB. Anyone know what that is? Few people, cool. It's a fantastic library. If you use core data, get off of it, you go to this instead. And Rx, of course, is pretty heavily used in this sort of model, and GRDB combines with Rx really well. And if you're looking to use Combine instead, the new framework from Apple, GRDB works with that too. On Android, we usually use SQLite with RxJava and Kotlin, but of course, the architecture components have most of these tools in place already as well. Right? So let's summarize. Building offline-first apps is hard. Hopefully, I've told you why. Don't do it if you don't need to. But offline-first apps can be great for your users for 2 reasons. One, they can offer a superior user experience with a low latency, and they are resilient to flaky networks. Some of the problems that we talked about, you have to deal with conflicts, you have to deal with inconsistencies, error handling is messy, and performance is something you need to worry about from the get-go. All right, with that, thank you. And if you have any questions, now's a good time, or I'm around as well.
OK, cool. So yeah, don't forget to go to the link and put some questions in the Slido, and vote for the ones that you think are the most interesting. So we got a few questions.
Cool.
One of the first ones is in terms of the difference between CloudKit and Firebase, in terms of how they merge conflicts. Is that something you can talk about?
I haven't used Firebase extensively, so big caveat there. My understanding, though, is that Firebase is more of a quote-unquote real-time thing, where it's intended to be used when you're online. And I think they support the obvious ones of doing latest writer wins and that sort of thing. The thing I like about CloudKit is you can either use the obvious solution that Apple gives you, or you can make your own, right? So I think they're sort of slightly different in terms of the perspective they approach it from a design standpoint.
And how would you go about making that decision in terms of when you're building a new app? Should you build your own thing? Should you use a tool off the shelf?
If you can avoid it, don't do it on your own. It's insanely hard, even on the server side. For example, this is another problem that the CloudKit paper talks about. You remember those change tokens we talked about and how they have to keep going up? Try doing that when you're dealing with a distributed system. That in and of itself is a huge problem. So if you can, use something off the shelf. Unfortunately, we haven't been actually able to do that because CloudKit is an Apple thing, and we have to support Android.
Do you actually know of any other CloudKit-style implementations that are outside of Apple?
I think Realm had something going a while ago. Seemed reasonable enough, but I haven't used it in production, so I don't know.
Switching gears, what kind of challenges do you see for offline in different kinds of apps, for example, like messaging or banking?
Excellent question. Banking is inherently hard to do offline well, because part of the issue is you have to find some way of letting users know when the data is real and when it's old. Right? So for example, obvious dumb thing, if I look at my balance and it says something, but it's 3 days old, probably misinforming me. And usually, visual indicators don't work that well. You can try and do some tricks, but nobody actually looks at it. So it's pretty hard to do with these sorts of apps. So you have to sort of think about it.
What about messaging?
Messaging, I think the obvious things that you should look at doing is supporting things like search and allowing people to look at their history quickly without having to wait to go online. To a certain extent, one thing you can do with messaging apps is rely on remote pushes more heavily. So typically, when you want to do some sort of sync, you make the remote push a sort of silent tap on the shoulder, and then your app is woken up, and then it actually fetches the data. Because messaging apps typically send minute amounts of data, they're small enough that you can usually send them in the payload. And those requests actually can happen on cellular, even with really low bandwidth connections. Apple's done a good job with that. That could be an option to consider. But yeah, you kind of stuck with the fact that if I have to send a message, I need a network.
Can you think of any verticals or types of services that are not good candidates for offline first?
Anything that's quote-unquote real-time, right? So, say you want to show financial information of any sort. Even that's not entirely true, because say you're a stock trading app. If your user is someone who's going to be making in-the-minute decisions, I'm going to sell this, buy that, whatever, then it needs to be online. But if it's more like a 401k type of thing, where you're probably monitoring once every 6 months, does it really matter if it's 1 day old? I don't know. Right?
And what about thinking about sort of these semi-offline situations? How do you think about that differently than the I'm on a plane in airplane mode?
The thing about doing semi-offline is either you're going to be online or you're going to be offline. So you can sort of try and think about it as, okay, I'm going to try and do some things in, where they work even if I'm not online. But the problem is the amount of complexity you bring in to support that is so high that you might as well just go the next 20% and make it fully offline.
And are there apps that you can point to that maybe other people wouldn't know that do this in a really good way that you think?
Yeah, several. 1Password is pretty great, and they actually do it across different sync systems, which is, I've never had a problem with their sync logic. Anything that's based off of CloudKit, in my experience, has been pretty solid. So Photos, Drive, Notes, all of that has been pretty good. Yeah, I'm sure there's loads of them out there.
And what about switching gears a little bit, thinking about from the design and product side? Like, how do you think that engineers should approach thinking about offline or intermittent connections when they're working with their peers from other disciplines?
I'd say think of it in a manner similar to security, right? So it's the kind of thing where you don't bolt it on at the end, right? It's not a feature that you say, okay, oh, and by the way, we're about to launch, let's add this on later. It's the kind of thing that you have to think about from the very get-go, because if you built it another way, making it work this way can literally mean ripping the whole app apart and starting over, right? So keep thinking about it from the very first minute, and know that if you're not going to make this decision in the very first day, you're going to pay for it later.
And do you think that there's what about products that actually offer offline as a paid feature, for example? How do you sort of deal with that when you have maybe some users who can use offline and some who can't, for example?
It's a good question. I don't really know how you do that. I mean, I'm not sure you can. This is a thing you can go out and sell as a big feature of the app, because it's the kind of thing where if it works, no one notices. But if it doesn't work, you're going to hear about it.
For example, like YouTube, where you can get offline content when you do that. Would you still recommend that the whole app takes this like offline first approach?
Content apps are a little bit different. I suppose the real-timeness of the data doesn't matter as much, so it might make sense to do that. But I'd venture that for things like YouTube or Netflix, those companies likely want to change the content that they show you fairly often, right? So it probably makes sense to have something cached, so you don't end up with a little white screen that does nothing for a while. But yeah, it's more about, I think, one feature of I'm going to plan to be offline, and therefore I'm going to have content saved, which is really different from a typical app, where the user doesn't have to go and say, oh, I'm going to be offline soon.
A couple more pointed questions. What about Realm DB for iOS? Have you any experience with that?
Some. I hope there's nobody here who works at Realm.
It's a safe space.
There's a few reasons I'm not a big fan of Realm. One, for the Swift developers here, value types. Realm doesn't do them. Second, I'm always a little hesitant about using something that Apple doesn't make and that I can't actually understand trivially, right? So if you look at the source code of Realm, it is insanely complicated. And while they're a fantastic company, I don't know how long they're going to be around. And the kind of apps we build, we can't really use them.
Okay. Another one is, what about, sorry, I had it here. How about supporting push updates for offline first apps? Is it possible to stay away from a pull strategy completely?
Pushes work if you can get them to work reliably, right? So if you're using something like APNS or Google Cloud Messaging, they don't actually make any guarantees that your pushes actually get delivered, right? So you can use them, but you then also have to sort of find a way to actually get the data from your own servers, right? So if you've seen apps that have weird badges where one of them shows 4 and then 5 seconds later it shows 2, it's probably because they're relying on those and they're not actually reliable.
And I've heard a lot in the hallway conversations, people talking about how to sell things internally. So obviously you have to come into some of these companies and sell this philosophy. How does that work? And what have you used to convince people this is worth the effort?
Show them examples of broken stuff. That's always worked beautifully, right? So there's a whole bunch of apps that don't work at all. I don't know about how the banking apps work here, but if they're anything like the ones that I see back home, where even if you have a fantastic internet connection, half the time they don't load, right? There's plenty of apps out there that just do not work this way. So show them examples of how it's broken, and usually people are pretty convinced by that.
OK, great. Thanks, Gopal.
Thank you.